Thank you very much, Wei, for the invitation to come speak at this symposium. It's been really fantastic. It's been fabulous to have the occasion to come visit, spend some time, and have this dialogue. And I'll say a few things in response to what we heard just before lunch, but this is not intended as an exchange with that focus. And of course, we can have more discussion later on and so on. And I think it's healthy to have different ways of approaching problems and so on. And I'll define what problem it is that we are trying to approach. And so I decided that we will share some highlights on work that we've been doing over the years on numerical simulation of shock turbulence interactions. And in this, I will try to stress some aspects of flow physics, turbulence flow physics that we have observed, and some ties to modeling. And this work would not be anywhere where it is without the heavy lifting that's carried out by these individuals that are listed. Johan, Soshi, and Ivan Bermejo Moreno were postdocs that were involved in different aspects of this work. And then at the bottom is a list of former PhD students who have actually all graduated now. So thank you for the invitation, and it's been really a great pleasure. So while it is still deciding its mind, I should acknowledge that resources for the work in terms of support for people came from different agencies and computer time, which is a crucial part of any investigation involving numerical simulations. So I would like to give a little bit of introduction, types of problems and where they come from, and some computational challenges. Ken stressed many aspects of these challenges. I'll highlight a subset of those challenges. And then spend a fair amount of time describing what I would call a canonical problem. It's an idealized problem so that we can really investigate in some detail what's going on. And then spend about 10 minutes or so talking about where this is going in recent years, where we have been considering a series of problems that have some engineering relevance. These are not engineering systems per se, but these involve elements of what high-speed flow systems may have in practice. So we could look at applications having to do with aerospace vehicles that move at high speed. In particular, if you're looking at hypersonic propulsion systems or high-speed supersonic propulsion systems and so on, they involve shock turbulence interactions, shock bound relay interactions, and so on. And if you look at sort of practical engineering methods that are used, such as the Reynolds average Navier-Stokes equations, there are serious doubts about accuracy of these methods, especially when you are considering geometry that may be considerably different from geometries that were used to calibrate models or to have models that then have successful predictions. As well as controlling shock bound relay interactions by involvement of bleed systems and so on provides a significant performance penalty and so on. This is an estimate from NASA. Operability of these devices is controlled by the stability of the shock train system. In terms of some phenomena that happen, turbulence is amplified as it goes through the shock wave. And of course, turbulence becomes anisotropic as it encounters a shock wave. And the whole problem involves the fact that the entire flow has a sort of a sloshing oscillation, a low frequency oscillation or a breathing oscillation where the size of the separated region grows and decays and the whole system moves back and forth and so on. So I won't get into the specifics of these particular applications, but let's see how we can model some of these phenomena and try to understand some processes in detail, and then we'll come back to problems of this kind. So here is an example of oblique shock turbulent bound relay interaction calculation. And there is an oblique shock that you can visualize. It's plotted in terms of temperature contours. And you can see that turbulence is energized as it is going through the shock. We can see the contour levels are rising up. Shock is oscillating in this region. This is one slice through the calculation, and this calculation itself was done a while back. And since that time, we have done these calculations for a variety of conditions, variety of shock strengths, a Reynolds number, and other parameters that may be of interest, and so on. So computations of such turbulent shock interaction problems provide a database that can then be analyzed to understand what it is that needs to be modeled if one is trying to do an engineering level model for this. So here is a different example. That of a jet which is choked is being injected in a supersonic boundary layer, and there is a bow shock standing in front. This is a slice through the middle of this jet which is being injected in a crossflow, again done a few years back, showing the features that you would have. This shear layer at the beginning of the jet is very unsteady and so on. The bow shock is very unsteady, and right under the shock there is a large region which is separated and so on, and the whole thing is unsteady. The barrel shock and so on inside this is highly unsteady and so on. And there are experimental images of these flows that were taken well before these simulations were done, which show these overall features that I have mentioned here. I won't have time to, for each example, show you detailed comparisons with experiments, but we take those very seriously and so on. So these are not meant to be just qualitative simulations. These are simulations that reproduce particular experiments, and in the references, these comparisons with experiments are carried out in quite some detail. Okay. So here is another motivation from a different class of applications where it's shock-induced mixing that is of importance. And in particular, Department of Energy has been interested in this problem of controlled nuclear fusion, where there is a cryogenic pellet of deuterium and hydrogen, which is about a centimeter size, and it's a very perfectly made sphere, which has layers of other materials coated on it. And then inside this chamber, this 192 sets of very powerful laser beams, this is at Lawrence Livermore National Laboratory, are all shining. The idea is that that will create a plasma around this shell, and that plasma will collapse this cryogenic capsule, and through this shock compression, extreme pressures and temperatures would be realized enough to create nuclear fusion in a controlled condition. That's the goal which is being pursued in the lab. What we can say is that obviously anytime there is interaction between a shock wave and some multi-material flow, even if the imperfections are mild, because of misalignment between interfaces and shock waves, there is vorticity that is generated, and that can mess up the degree to which you can create nice compressions and so on. So overall efficiency of these devices can be significantly impacted by turbulent mixing that is generated by shock-induced mixing. Of course, in astrophysics, there are other applications that involve these kinds of processes. So having described some applications to give you a flavor of kinds of problems that may be of interest, let me talk a little bit about one particular challenge that we see. And this is a computational challenge which arises from the realization that we are interested in a broadband turbulent flow. And so numerical methods that do a good job of resolving turbulent motions, which are essentially methods that are spectral methods or high-order methods that represent a large range of scales accurately, that comes in conflict with the requirement of capturing shock waves, because for shock capturing, you need numerical dissipation around the shocks and sharp interfaces that may be present as well. So then the question is, how do we resolve these conflicting requirements? Is there a pointer I could borrow? This one here. Yeah. So the idea then that we have is to combine numerical methods that are designed to do these things in a surgical manner or in a solution adaptive manner, where we're using essentially a second order central differencing or sixth order compact schemes in regions where we have turbulence, and then where there are shocks, we are using methods that are well designed for shocks. And if these methods are directly applied to regions of turbulence, they are over-dissipative. They would damp many of the finer scales that we want to represent. And of course, it's important when we propose any method of this kind to evaluate it carefully and so on. And I won't have time to discuss these and so on, but these have been discussed in detail in literature. We have many papers and so on. And if one of you is interested in more details, we can sort of talk about that offline. But one needs to carefully evaluate numerical methods before you can establish trust in the calculations. So here, is what I call a canonical shock turbulence interaction problem. What we have here is we have isotropic turbulence, which has been computed, which is flowing into this domain. Downstream boundary condition has a higher pressure relative to the upstream boundary condition, and the variables are such that it would hold a stationary shock, nominally stationary shock, in this domain. And the idea is that the shock is nominally planar. The interaction of turbulence causes distortion of the shock. Turbulence as it passes through the shock is modified, and it's a fully coupled system that we want to study. And so what are some of the parameters that we want to look at? One can describe the Mach number of the approaching flow, the Mach number associated with turbulence in that approaching flow, and of course there is a Reynolds number associated with the turbulence overall. But then since it's in a compressible medium, we also have to characterize the entropy fluctuations and the acoustic fluctuations. There's a shock which has a finite thickness, and one may need to think about the thickness of the shock relative to the integral scale of the turbulence. And of course, in any real gas, there may be real gas effects that may be required to be considered as well. So in Ken's presentation, the focus was on regimes where real gas effects and other non-equilibrium effects are very important. Those are not the regimes that we are describing here. We are thinking about engineering applications where Mach numbers may be supersonic or maybe Mach 3, Mach 4, and so on. Temperatures may be high, but they are not as high as you would have in terms of re-entry application and so on. So we believe that continuum models are adequate for these aerospace applications, not near space outside Earth's atmosphere, but for engineering systems that we may devise to come up with propulsion systems and so on that are air-breathing systems. And so there one can make estimates of shock thickness relative to the integral scale associated with turbulence, and one can make the argument that the molecular mean free path and shock thickness are comparable. They scale in the same way, and Kolmogorov scale is dictated by the Reynolds number that we have of the turbulence. And so if we make estimates for engineering problems of the kind that I've been talking about, one can argue that the detailed shock structure is not really the key part of the problem. The turbulence phenomena that one is interested in describing are continuum phenomena, or you could say they are hydrodynamic phenomena and so on. And therefore, Navier-Stokes equations are the basis that we are using to describe these calculations. And so what is animated here, let me stress, are contours of vorticity. Vortices are visualized by using the Q criteria. And you see many colors here, and that's because we have colored a particular isosurface which is identifying strong vortices by its orientation relative to the main flow direction. And so all the different colors indicate here is that these vortices have a random orientation, or is isotropic turbulence. But then this isotropic turbulence, as it goes through the shock, we see that is much more red here downstream. And that's because now there is a preferred orientation for these vertical structures just downstream of the shock. And so this is something that we can see here directly. But let me take just a moment to try to explain what is the physics. Why is it that these vortices are getting oriented differently downstream? And a very simple way to think of it is to think about a fluid blob, a spinning fluid blob, which essentially is a fluid vortex. And as it goes through the shock, we can argue that the angular momentum associated with the spinning blob is essentially going to be conserved. I mean, the only reason it would not be conserved is because of baroclinic torques that may act. So one could make an estimate of baroclinic torques, but for primary purposes here, we can ignore the baroclinic torque. And so if angular momentum is conserved, then it is the component of vorticity or components of vorticity which are in the plane of the shock. They are the ones that are magnified by that fluid element going through the shock. And vorticity component, which is normal to the shock, is unaffected by its passage through the shock. So this is what makes the turbulence strongly anisotropic. So we can quantify this by looking at the RMS of vorticity components. One is the component in the direction normal to the shock, and 2 and 3 were the components in the plane of the shock. All components are equal. This was isotropic, and then the transverse components are amplified through the shock. And so just downstream of the shock, one has a vertical flow where 2 components of vorticity are very strong compared to the normal component. And then, of course, turbulence is strongly nonlinear. Vortex stretching and tilting is the key process in turbulence. And so turbulence doesn't remain in that anisotropic state. It returns towards isotropy as far as vorticity is concerned. And some distance downstream, now all components of vorticity are about the same, and it's decaying away. So this is what we are able to observe in these present direct numerical simulations. In the past 10 plus years back, we had also done calculations of the same problem, and then domains were not long enough, and numerical methods did not have enough resolution. We were not able to do calculations on grids that we are able to do now, and Reynolds numbers that we are able to achieve. I mean, Lex would laugh at these Reynolds numbers being small, not high Reynolds number, but I would say this is progress compared to time 1993 and so on, where Reynolds numbers were 15, 20 or so. So there is some beginning of separation between inertial scales and dissipative scales and so on. So one can call such flows turbulent, whereas flows at lower Reynolds numbers like 20 or so are not really turbulent in the sense that they don't have a broad range of scales. They have just one scale. There is now beginning to be a scale separation, which is a required element for something to be called turbulent. Okay, so we then ask how good is theory in predicting this amplification that we have just observed. So it's possible to do a linear analysis where the turbulent flow upstream of the shock is represented in terms of a synthesis of Fourier modes with different orientation. You can synthesize a turbulent field as a superposition of Fourier components. Each Fourier component is convected by the free stream velocity upstream of the shock. Then downstream of the shock, one needs to solve the linearized governing equations, and the shock is to be perturbed by the presence of the disturbances, a linearized perturbation, and it's possible to then solve the downstream state in combination with the shock perturbations, which are essentially the linearized version of the unsteady Rankine-Hugoniot conditions. And one is able to solve all that, and this was done back in the early 1960s. Harv Ribner in particular and Frank Moore at Cornell and others have done extensive linear analysis, and we can use that to estimate what turbulence should do. And so in here, this curve is Ribner's theory. This is the ratio of the turbulent kinetic energy downstream divided by the turbulent kinetic energy upstream as a function of Mach number. And so as Mach number increases, turbulence amplification increases. And so the symbols that are plotted here are results from our numerical simulations. It is very, very difficult to experimentally observe or create this flow. There has been a phenomenal effort in the past, and I think if there can be more efforts, it will be really nice to have more data from experiments. But here is one data with a large uncertainty bar available. However, while the overall turbulent kinetic energy amplification is well predicted by this linear theory, if you look at some details, this is an anisotropy. The 1 component, or the component in the streamwise direction relative to the transverse component, according to theory, is amplified more in the streamwise direction and less, or the transverse components are amplified more. That's not what is seen in the simulations. And so why this is because of the nonlinearity that I mentioned, that turbulence becomes nonlinear, and linear theory is going to predict this, which is not what is observed. And this is a topic that has been taken up later on in more recent publications as well. So one further aspect that we want to highlight associated with what we are observing is, in some sense, a detailed view of what is happening to the disturbances as they interact with the shock. So the shock gets highly disturbed. There are times when there are shock-shock intersections, and there are these transverse waves and so on, triple points coming up and so on. If we look at this animation, you can see that when there is a red blob which has a positive or stronger streamwise velocity, shock gets pushed in the downstream direction. When there is a large blue blob, then the shock gets pushed upstream or becomes concave in this situation, and these waves are interacting with each other and so on. So that's sort of the overall behavior. When U prime is strong, a shock gets stronger, it creates a stronger compression, shock is downstream, and the reverse situation is true when we have this shock propagating upstream. So we can imagine that if turbulence were strong enough, there would be regions where U prime is sufficiently negative that maybe shock might disappear. So this raised a question, what is sort of the regime diagram? One is familiar with regime diagrams in different types of flows. For example, in combustion applications, depending on the turbulence intensity and length scales, one is able to create different regimes. So then the question is, what happens for shocks? Are different regimes possible? And so what we find is, in fact, as anticipated in work of Hesselink and Sturtevant, they observed in the experiment done in a shock tube with SF6 and a light gas combination with shock waves traveling through, that there were times when they would have a peaked profile where there is an overshoot and then it returns back, versus situations where it's a rounded profile is what they call it here. That is a similar signature that we observe. There are times, so these are traces taken along particular Lagrangian trajectories, if you like, through this interaction. Fluid is coming along, fluid parcel is coming along, and as it goes through the shock, it is over-compressed by a large amount, and then it relaxes back towards the Rankine-Hugoniot mean state that it eventually achieves. There are times when a fluid parcel comes along, there is no shock. That fluid parcel is compressed in an isentropic manner through along that streamline and so on, and goes to the downstream state. So what we are finding is that, in fact, it is possible, as suggested by experiment, that one can create holes, or one can quench the shock locally. And then the question is, can one classify this? Can one understand when one of these situations is going to arise as opposed to another? So through these simulations, we are able to classify the outcome in terms of a regime which we can call broken shock, or where we have shocks with holes, and regime where we have wrinkled laminar flames. These are wrinkled shocks where the shocks are distorted by the interaction with the turbulence. And so in terms of coming up with a criteria, we can think about criteria that are based in the fluctuation Mach number and the mean Mach number of the shock. And we can see that there's clarity in this picture if we are to categorize this interaction in terms of, this is a criteria that we had previously proposed, where we said that if the pressure fluctuation associated with the turbulence is strong enough compared to the pressure difference across the shock, then we would break the shock. We would essentially create holes. Thinking about this more, this is the criteria which is more effective, and that's what's shown here, is that when the fluctuation Mach number exceeds some constant times the Mach number difference, the degree to which it is supersonic upstream, which is basically a finite probability of having subsonic flow. Once there is a region of subsonic flow locally, then the shock disappears in that region and so on. One requires a supersonic flow everywhere and so on in order to maintain the shock. And so this is, you can see that when this threshold is exceeded, one has a broken shock regime. These are the different simulations that were carried out. If we are trying to categorize the broken versus wrinkle regime using this previous parameter, one doesn't have as clear a breakdown. But here you have the wrinkle shocks, and then above this threshold you essentially have the broken shocks. So one can, of course, study these phenomena in more detail and so on, and I leave you to reading the papers and so on if you're interested in this particular problem. I thought I'll mention a few variants that we have considered. So with Ankit Bhagatwala, we carried out a study where we are interested in interaction of a blast wave, a spherical shock which is spreading spherically, and is traveling through a medium. And this is an old problem studied back at the time of Sedov and Taylor and so on. This is the Second World War time frame and so on. G.I. Taylor came up with this prediction of coming up with an estimate of the yield of a nuclear weapon by simply the images or photographs of the blast wave that was observed. These blast waves are traveling through an ambient medium or a uniform medium. The question is, what is the change that happens if you have turbulence? And so this is compressible turbulence into which we deposit energy to create a blast wave. And then there are parameters. We can make the blast wave weak compared to the turbulence, or turbulence is strong compared to the blast wave, or they can be comparable or strong and so on. So just as what we had in the previous case, this is now a geometrically different situation, but otherwise analogous problem. And so, of course, shock spreads. G.I. Taylor's 2/5 power law for the radius of the shock as a function of time is something that we continue to observe. But depending on how strong the turbulence is, one may have the same regimes that one talked about. So there's one important difference in this spherical problem relative to the planar problem, which I want to stress, which is that in a blast wave, you don't just have a high pressure following the shock. There's also a strong rarefaction wave that any blast wave must have. This is the mean density profile. Density rises through the shock, and then look at the magnitude of this rarefaction wave that is behind, and so on. This was the original density. After the rarefaction, density has been brought down that strongly. And so this blast wave, when it interacts with the turbulence, is going to be interaction of a shock followed by an interaction of a rarefaction wave. Both have to be considered in order to come up with the overall effect. And so let's see what we learned from this simulation. Here we are plotting some contours of vorticity for a strong shock and a weak shock interacting with this background turbulence. And so what we are finding is that as a strong shock passes through this isotropic turbulence, it essentially extinguishes the turbulence. And that's because of the strong rarefaction that is followed by the shock, which essentially eliminates the turbulence entirely. Of course, in here, another effect that is taking place is the fact that Reynolds number of the flow has dropped tremendously in this blast wave region, in this rarefaction region. When you have a weak shock, then this little blue region here is the region that is left behind, but you cannot tell in these contour levels that there is actually a shock. And so let me highlight that by going further. Of course, it's a weak shock, so you shouldn't see any significant change in vorticity. It's only a very mildly change. This would be the regime that is of interest if you're thinking about a sonic boom propagation through, say, an atmospheric boundary layer. Then the pressure fluctuations associated with the boom itself are small compared to the atmospheric turbulence. So depending on the strength of the shock relative to turbulence, one can ask, is the shock distorted by the turbulence? And if the shock is strong, then it will not be modified. And so here we quantify it by looking at RMS deviation in the shock radius R sub s is the mean radius, R sub I is the instantaneous radius, and so this is the degree to which the shock is wobbly compared to a mean spherical size. And so the larger this number, we can call this asphericity because it's normalized by the mean radius here. So the larger this number is 10 to the minus 3 and 10 to the minus 4 and so on. It's very mildly aspherical. When the shock is weak, then turbulence is able to create significant asphericity as that turbulence is decaying and the shock is running outwards. So I want to switch gears just a little bit here and talk about yet another variation. You saw that animation run where if I go back and come back here again, there was the shock and it collapsed and then it bounced back. A converging shock passing through a region of turbulence, and then from its most focused point, it retracts back, it bounces back. And so any material is going to encounter two shocks, one which was converging shock and then expanding shock, and that we can describe here in terms of a XT diagram or a RT diagram, if you like. This is the radius at which the shock is. A shock is converging, and then it's bouncing back. This is the shock from the other side approaching. This is when you have the most dense material, and then a shock is expanding outwards again. And there's a region here which is left behind, which is a region where entropy has been very dramatically changed and so on. All right. So let's look at this a little bit more. This is also published in detail now. There is a well-known solution to the Euler equations, which has a self-similar solution which has a singularity at a finite time. This is the converging shock, which according to Gurulai's similarity solution behaves in this particular way, where radius has this power law behavior where alpha is theoretically predicted to be a certain value. And so we do fits to the data from the simulation. The fit is shown over here. The flat portion here on this log-log plot would give you this exponent. And we are seeing that these exponents are actually in pretty good agreement with what is predicted using Gurulai's solution. Gurulai in the self-similar solution makes a number of assumptions, and one of the assumptions is that it's an infinite strength shock. That is the assumption under which this self-similarity solution is obtained. And of course, the shock is getting stronger and stronger and stronger as it is focusing, and so it's a decent assumption for times when the shock radius is really small. And so it's no surprise that that is a good description of what happens. Of course, turbulence is strongly being modified. This is initial stage where the shock is shown by contours of dilatation, and the background colors are in terms of vorticity, and the shock converges and then bounces back. And when it is back at the same mean radius that we had before, we are looking at turbulence plotted with the same color bar and so on. So you can see that when the shock has come back to the same radius that it originally was at, a turbulence that is left behind is much more energetic. So this process of shock compressing this turbulent flow and then recompressing again, because it's creating this turbulence on both passes, the inward path as well as the outward path, and so one has a very significant turbulence behind. And so we can quantify this in terms of ratio of vorticity after the shock relative to the initial vorticity, velocity fluctuations in the shock normal direction relative to upstream and so on. And here is a case where one has very clear, very marked shock amplification of turbulence. In the early stage, this is when it's launched, and then its ratios of velocity fluctuation, kinetic energy is about 5, 8, and so on. And then after a second pass through the turbulence, it's even much larger, and so on. So There are very clear anisotropic effects that can be seen in these simulations, and of course one can try to see what engineering models for turbulence using Reynolds average Navier-Stokes equations would do, and it's these effects that are missing from traditional RANS models and so on. So here is one way in which information is available that can be used for improving these models, and we have pursued some of that, but we can talk about that later on. I want to indicate that these problems in spherical geometry are much more challenging than the isotropic turbulence problems that I described. Reynolds numbers that we have here based on the turbulence integral scale and the velocity fluctuation are modest. If we make an estimate of square root of this Reynolds number as essentially RE lambda Reynolds number, these you can see that these are modest Reynolds numbers. These are not high Reynolds numbers, not as high as they were for the previous problem. So I want to now describe how we are moving towards engineering applications involving shock turbulent boundary layer interactions. I described the canonical problems and some variations on these canonical problems. Of course, a problem of an oblique shock turbulent boundary layer interaction is one that I showed you a movie from at the beginning, and that's something that's described in detail in this work, where this database is also used to evaluate turbulence models. And in particular, what is found is that what is missing in the RANS models is the degree to which anisotropy is not correctly predicted. It is the Reynolds stress anisotropy which is not well predicted. And so if we use a more sophisticated turbulence model, such as the second moment closure, which actually carries transport equations for Reynolds stresses, it is much more successful in predicting this oblique shock turbulent boundary layer interaction. So that's described in this paper. I will not get into that detail and so on. After doing studies of this oblique shock turbulent boundary layer interaction, we've also carried out studies of problems that are mentioned here. A problem of a shock train in a constant area duct, which is sort of a way of creating a process to slow down a supersonic flow or supersonic diffuser. And I'll show one or two highlights from these studies as we discuss. Compression ramp flow is something that we have done more recently, and this is where actually a fantastic help from Lex's group has been very, very valuable to us. They have in the past on this problem as well as many other problems done very extensive, very careful measurements, and they have been very kind to share all the data and so on. So we have really benefited from studies that Lex has carried out on these problems. So I want to say a few words about these problems as we go along. Thing that I want to stress is that applications really have moderate to high Reynolds numbers. And if you think about the overall flow in terms of moderate to high Reynolds number, the cost of resolving the near wall scales, which is what we would call wall resolved large eddy simulation, where the eddies close to the wall are resolved, those are very high. The cost, just the sheer number of grid points and the computational cost is very high, and therefore at present time, when we are doing studies that I would call scientific investigations, where we want to be sure that the physical processes that are taking place, we are resolving them. So a wall resolved large eddy simulation of these problems at the moderate or high Reynolds number is still not possible. And so we lower the Reynolds numbers by roughly a factor of 5 or so compared to the experiments. At Princeton, Lex has done experiments at conditions that can be duplicated by wall-resolved large eddy simulations, in particular for compression ramp flow, and we do compare with precisely the same conditions that are done in the experiments. So I'll come to that. But there is a great need in future to, this is something that is going on a lot in the community these days, but to continue to develop these hybrid methods which allow the high Reynolds numbers to be made accessible by these simulation methods. So here is a highlight from a shock train calculation in a constant area duct. This is a constant area duct. The flow is supersonic here, and some downstream pressure boundary condition is imposed. And in this constant area duct, a system of shocks get generated. It's a fully three-dimensional problem. This is a cross section. This is the long side of the duct. It's a rectangular duct, and cross sections at different stations are plotted over here. Initially, you have boundary layers on all sides like so, and these boundary layers are growing, and this core region in between is essentially disappearing. Ultimately, downstream of here, there will be essentially a duct flow, which is a subsonic duct flow. The downstream flow is subsonic, and I didn't pull out lots of detailed plots and so on, which you can find in Brandon Morgan's publications, in particular this work here, where we study. You can see that the shock structure is modified as you approach the wall. You have lambda shocks in both directions. A boundary layer senses the presence of the shock upstream of the shock in both directions and so on, and flow slows down, then reaccelerates, and then goes through another shock and so on, a whole series of shocks. And so one can try to compute this using a variety of turbulence models, SST, Spallar Lamaris, K omega, with different modifications. And this is the reference LES that we're comparing to. And while they all have shock trains, of course, they are not comparing well in terms of we have the same overall boundary conditions, but the place where the shock train sits and then how it dissipates, how the flow is changed, is different depending on the turbulence models. So of course it's possible to then twiddle the constants, if you like, in these models and make it come closer to this LES, but our philosophy has been that here, since we have captured the phenomena using first principles, can we overcome the difficulty of high Reynolds number flows by minimal modeling, where the near wall regions where the eddies right close to the wall, which are the ones that are most cost constraining, if we model just those, then we would be able to capture the physics in high Reynolds number flow directly by using a wall model large eddy simulation. So that's the approach that we have been taking. So here is, in fact, the calculation duplicating experiments of Ringet et al. This is the experiment done at Princeton, where the RE theta is about 2000. It's approachable by large eddy simulation, which is well resolved. It's a full three-dimensional configuration with this compression ramp with these aerodynamic fences that contain the flow, which is then compressed by the shock. And the detailed geometry as well as the experimental data were shared by Lex and Matthew, and we're grateful for that. And here are a few results that from this large eddy simulation, which is wall resolving, are shown. These are pressure contours and skin friction contours and skin friction lines here at the bottom. And you can see that, in fact, an approximation where you can say that over 80% or more of the width of this test apparatus, the interaction is essentially two-dimensional. There are strong regions near the aerodynamic fences where the flow is significantly three-dimensional, but I think the purpose of these fences to create a region of significant two-dimensional flow is very well realized in this particular design, and that's the comparison that we have carried out in detail. And here's a three-dimensional visualization or rendering of this experiment. You have this turbulent boundary layers with the forests of lambda vortices and so on, as were discussed in the morning, which are going through the shock. The thing I want to emphasize is that there is a strong vertical region here. Flow separates. There is a corner vortex also that is created, which is lifting up. And as we take different cross sections, we will see shocks in this region close to the aerodynamic fence. There are shocks that are starting where the fence begins, which modify the flow significantly. So if we look at this in the next slide, these are cross sections taken progressing downstream. The left edge is the location of the aerodynamic fence, and these are different quantities. It's the streamwise velocity, the vertical velocity, and the span-wise velocity, and so on. So the flow is significantly three-dimensional. These are turbulence components, and one can use these data to improve modeling from engineering predictions. And so I want to wrap up by showing this example where Britton-Olson's work of a turbulent flow going through this overexpanded nozzle where the downstream pressure is not matched with the pressure at the exit. And since because of this mismatch, shock forms, and the shock interacts with the boundary layer, causing a separation of this shock, and the conditions are such that the separated flow never reattaches inside the domain of interest, and this is duplicating conditions experimentally studied by Dmitry Papamushko and Johnson. These are the geometrical parameters. This is at a modest Reynolds number in the simulation. The experimental Reynolds number is much higher than this. And you can see the processes that are taking place, that as the shock moves upstream, its interaction causes the separation to be intense, and the shear layer spreads. The blockage that is produced downstream influences the pressure that is seen downstream, which communicates upstream with an acoustic wave propagation and so on. And this whole process is a dynamic process. It keeps adjusting and never is able to settle down. It keeps oscillating and so on. And so the purpose of putting this up is that it is possible to conduct simulations where turbulence, shocks, acoustics, and in future other aspects such as structural coupling and so on, heat transfer and so on, can be described using numerical methods that are doing reasonable justice to the phenomena that are being described. And so I didn't put lots and lots of slides to show comparison with these experiments, but that is something that you can find as you go to these papers. So let me wrap up by summarizing some of the observations that I have made. It is useful to think about canonical problems as well as problems that are more applied. Canonical problems allow study of physics in a more clear sense. And so using these canonical problems, we were able to learn a number of things about the interaction of turbulence with shocks. And I mentioned the fact that vorticity becomes anisotropic and returns to isotropy rapidly. And this is a part which is missing in the theory, and that is why theory is not predicting this. And so there is need for theory for doing this better, as well as extension of theory to non-planar regimes. The problems that I described to you of shocks interacting, a spherical shock running through turbulence, or a converging shock running through turbulence and bouncing back, there is no linear theory available for that problem and so on. And it's a nice problem that can be done. I stress the fact that it's possible to have regimes where shocks weaken to the point of disappearing, and one can understand why that happens and so on. I just stressed these problems here. And finally, we've seen illustrations that large eddy simulation as a tool for engineering applications in regimes where there are significant interactions with shocks and turbulence is a very viable thing. Of course, the challenge of going to higher Reynolds numbers of applications, is one that we continue to work on. And it is not a solved problem in terms of going to high Reynolds number with these applications of interest. It's not yet a demonstrated tool, and there are many approaches that are being developed. Hybrid methods is one good candidate for that, and I think Ken may have a different view in terms of how he approaches that, but we believe that for these applications of engineering interest, Navier-Stokes equations are sufficient, and therefore numerical methods that are then trying to solve those Navier-Stokes equations. Of course, there is a turbulence modeling problem that we encounter at small scales because there are subgrid scales that in the near wall region are energy containing scales. They are subgrid, but they are not dissipative scales alone. They also carry significant energy. And so how to model that in an effective way in flows where there is coupling in terms of it's not an equilibrium boundary layer, it's a boundary layer which separates and reattaches. And so to accurately predict outcomes of such engineering problems in a reliable fashion where you can say that there is a certain error that, or if one could say that uncertainty in the prediction is 2%, 5%, 20%, one wants to be able to ascribe uncertainty to engineering predictions as well. And so that's a task that very much is of interest in the present efforts. And this is my very last slide in terms of where these activities are going in future. Of course, multi-phase flows and so on with other effects and so on, and some of them were mentioned by Ken, multi-fidelity modeling going towards exascale computing, and I just was stressing this. And so we see that high-fidelity computations do provide a role in engineering design and analysis. Of course, they are not the tool where it's just one tool that will solve all problems. Engineering problems require a combination of tools, simple tools that provide quick estimates, and way stressed in the morning the idea of surrogate models and so on. And one can drive or derive or come up with reduced order models or surrogate models using information from different sources, high fidelity simulations or experiments, and combining them and so on. So thank you very much. I'll close at this point. And
I have Reynolds number.
Yes.
If
Yes.
you really go to small scale,
yes.
actually the Nielsen number is not small. If you go to small vortices. So in that case,
No, I disagree with that observation. Knudsen number for turbulence, even if you evaluate based on Kolmogorov scale, it is small. And this is something that is discussed in chapter 1 of Tenekes and Lumley.
But we in the DSMC, they did some calculation. They found that if you Reynolds number, for example, only a few hundred, the small scale, they can go to the Nielsen number like 0.07. Is
0.07.
Yeah, it's now
0.07 or
0.07. But that one is a low speed.
yes. Well, actually, with a colleague of mine, Don Baganoff, who used to work with DSMC, he and I shared a student, and we did studies of compressible isotropic turbulence as a function of Knudsen number, and we didn't find much effect in the studies of isotropic decaying turbulence. Of course, they were not at high Reynolds number. They were at Reynolds numbers that could be afforded by the computations that we could do. So I'm not saying that if we consider applications maybe that have different origins, say astrophysical origin, or have connections to reentry or really hypersonic applications and so on, that there may be regimes that are not described. I mean, clearly there are regimes, there are more complex phenomena that are not described in Navier-Stokes equations. I'm not disagreeing with that. I'm saying that Navier-Stokes equations provide a sufficient set of physics that.
How do you know that?
How do you know that is anytime, well, let me make a statement that is sometimes attributed to Einstein. I'm not sure whether that attribution is correct or not, that all models are wrong, some are still useful. And so Navier-Stokes equations are not an exact representation of nature. They are an approximation. And to the extent we can understand what is the limitations associated with those approximations, we can use it with some confidence. That's what I think all modeling is about, is understanding what is useful and stay away from when it doesn't work, then we need to extend it. We need a better model.
I would actually agree with this statement. And I love this last sentence. incorporating high fidelity computation engineering design. I would add it, even low fidelity sometimes is useful.
It is. I didn't have it here written, but if you, I did say low fidelity is useful. I am not saying that low fidelity should not be used. Low fidelity and high fidelity. Often, as far as optimization is concerned, you want to use what is needed. You would not use something that's not needed.
So, Jim,
Yeah.
For your shock and anisotropy interaction, you basically say ignore the clinic term.
Yes.
But considering the instantaneous nature of
Yes,
the
yes.
shock lift, so what kind of contribution you think is
Well,
considering the scale of the vorticity?
So I said ignore it in terms of explaining the overall change in vorticity. Of course, simulations don't ignore it. Baroclinic terms are part of the Navier-Stokes equations. They are accounted for. And there are other problems that I didn't, because I had to choose things that would fit here. We have done problems of interaction of shocks with density interfaces which are perturbed. And then, of course, the mixing is dominated by baroclinic torques and so on. So I could show you some of those later on. So those are important, and of course one needs, in terms of engineering models, one needs a representation of those effects, and I think community is far behind in terms of engineering models. Certainly high fidelity models can be done, and that's been successful.
The value of these computations is that you can actually tell us at what level they come into play, right? Because obviously in the compression rate expression, if you have a big shock or an incident shock, you're going to have a contribution from the variability.
Correct. We can, from the simulation, we can evaluate the degree to which they play a role.
For the Mach number, the density ratio we're seeing and the fluctuation.
Yes, yes.
And then I say, of course, solenoid and baroclinic, these are two things.
Correct. Yeah.
And the other thing I think just comparing the Reynolds model,
Yes.
shock trend,
Yeah.
why the large eddy simulation results seem to dissipate faster for the shock trend?
That's a question about why RANS does what it does. I'm reinterpreting your question.
Yes.
So RANS models, there are many aspects of RANS models that should be discussed. I stressed the anisotropy. Turbulence and anisotropy is not very well captured. And so in particular, in these shock train problems or in oblique shock boundary layer interaction problems and so on, the size of the separation region and so on that is predicted using RANS models is too large compared to what is either observed experimentally or when we do the higher fidelity simulations. And so that intensity of the separated region and the scale is missing, and so that is influencing the recovery.
Usually I thought the predicted eddy viscosity tend to too large.
Yes,
but
yes.
That seems not to be the case.
Well, in the problem of, so of course, I think it's, when one is making comparisons, it's very important to also ask the RANS calculations that one is comparing to, were they grid converged? Did they do sensitivity studies, near shocks, and so on? And this is something that is being done more and more in the community and so on. And as this is done, and in particular, I think there are adjoint-based methods and so on that are being used to do these RANS calculations with refinement in regions where there is a greater sensitivity and so on. So I think I can't give a very simple, crisp explanation as to why the RANS model is doing something that it is doing. We are using it to make contrast relative to, on one hand, different RANS models and how it compares to the high fidelity simulations.